Hello everyone. We are here to record lecture 9 at the course Automata and Formal Languages. We are currently at unit 7, part 2 of the lecture, and today we will talk about context-free grammars, regular grammars, normal form of the grammars, closure operation over grammars, and hierarchy of Chomsky for grammars. I would like to remind you that any finite language can be constructed by a context-free grammar. Let L be a some finite language with Wi, where I is less equal to n, and Wi belongs to sigma star. We can construct the following grammar. S derives the first word of the grammar, S derives the second word of the grammar, S divides as the next word of the grammar until the last word of the grammar S derives Wn. We can ask ourselves several questions. Are the regular languages can be constructed by a context-free grammar? Are the regular language a subset of context-free languages? And we will answer in several minutes' time. First, let's define a regular grammar. A grammar is called regular if each production has one of the following forms. A derives W or A derives W concatenation B, where W is some word over sigma star and A and B are variables. Let's see an example. In this grammar is a regular grammar. Why? S derives only terminal symbols 0, 1, 2. Then S derives a prefix which is terminal symbols 0, 1 and the suffix which is a variable A. A derives 0, A or 0 or epsilon. This grammar is regular because it holds the previous definition. A grammar is called simple regular grammar if each production has one of the following forms. Variable A derives a single letter sigma, or variable A derives a single letter sigma concatenation with new variable B. Each regular grammar can be modified into a simple regular form. Let's see how we can take the previous grammar and transfer it into simple regular grammar. So when we have at the right hand side two or more symbols, two or more terminals, we just add additional new variable. Instead of S derives 0, 1, 2, S derives 0 and the new variable B. New variable B derives currently 1 and 2. S derives 0, 1A now replaced S derives 0C. C derives the rest of the rule, which is 1A. A derives 0A is a correct form. A derives 0, wonderful. A derives epsilon, once again, very good. So let's rewrite the rules for variable B and variable B. B derives 1, 2 is not a correct form. So we rewrite it. B derives 1D. And from D we derived the rest of the rule, which is 2. The new grammar is simple regular grammar. Let's talk about additional theorem. The set of languages that have a regular grammar is the set of regular languages. The proof idea will be the very simple idea. Given NFA, we can create an equivalent regular grammar. Given a regular grammar, we can build an equivalent NFA where each rule of the grammar will be a transition from one variable to another variable, and so on. So let's start from moving from NFA to regular grammar. We will use the following lemma. A regular grammar, RG, can be constructed by non-deterministic finite automaton. The basic idea without any proof will be the following one. We will translate the transition function of NFA into rules of the regular grammar. Each transition will be translated to a new rule. The algorithm how to convert NFA to regular grammar will be the following algorithm. We will rename all states of NFA to a set of capital letters. Usually initial letters of Latin alphabet. Name the start state of NFA by S. Each transition delta A sigma equals B will be translated to the rule A derives sigma B. And each transition A epsilon equals B, delta A epsilon equals B, will be translated into A derives B. For each accepting state A in NFA, we will add additional rule A derives an empty word, because it is the meaning of an accepting state. Let's see an example, and I advise you to try to solve this question by yourself. First thing, we will rename the states, and QFS will be S since its initial state, and Q1 will be A. So after renaming the state, each transition should be translated into the grammar. We have a self loop with 0 from S to S. So we will add the new rule S derives 0S. We have additional error from S to A with 0 and 1. So we will translate it into two rules. S derives 0A, S derives 1A. Since S in accepting state, we add additional rule S derives an empty word. Now we define the rules for A. We have a self loop with 0, so we will have A derives 0A, and we have an H with 1 moving to S, so A derives 1S. This is a regular grammar for given NFA. Okay, let's start talking about other direction. We are giving a regular grammar and we want to construct an equivalent NFA. We will use the following lemma. An NFA can be constructed for any regular grammar G. The basic idea will be, once again, without giving a formal proof, we will construct a state for each variable. We will define the transition function according to the right-hand side of each production rule. And we will use the following algorithm. We are giving a regular grammar G. We will transfer all rules of the grammar to be written in a simple regular form. So at the right-hand side, we have a single letter and single variable, or only a single letter or epsilon. Denote the simple regular grammar by 4 tuple V sigma, S, and R. Now, the equivalent NFA is the set of states will be equal to the set of variable. The starting state will be the starting variable S. For each rule of the type A derives CB, we will draw a transition, an arrow, a transition from A to B. We will add delta A C equals B. For each rule A derives B, we will add epsilon transition from A to B. delta A epsilon equals B. Now we have to decide which states are finite states. So for each rule A derives C, we will add new state F to Q. This state will be a final state. We will draw a transition function from A to we will draw a transition from F to from A to F with the letter C. Delta A C equals F, and we will add this new state F to the finite states and also to all the states Q union with F. Once again, I encourage you to solve this question by yourself. We are giving a grammar, a regular grammar, but not in simple form. So we will transform this grammar into the simple form. We have only one rule that is not okay. S derives 1a. So we will rewrite this rule with A derives 1b and B will derive 1 and A. The resulting NFA will have three states initially, S, B, and A. We will have a self loop with 0 from S to S. We will have a transition from S to B with 1. From B to A with 1. We will have a self loop from A to A with 1. And A derives 0 will be drawn to a new state F where the H between A and F will be the H with 0. Some conclusion about regular grammars. Regular languages is a proper set of context-free languages. So if we are looking at the set of all context-free languages, regular languages will be a proper subset. Additional topics for today will be context-free closures. We will talk about union, concatenation, clean, star, contents-free languages, substitution, intersection with regular languages, and we will start talking about normal form of the grammar. We will use a Chomsky normal form. Exist other normal forms, but we are not interested in them. And we will talk about Chomsky hierarchy for the grammars. Let's talk about some operation over grammars. The context-free languages are closed under the following operations: union, concatenation, clean star, intersection with regular language, context-free language, substitute. The context-free languages are not closed under complement or under intersection. So let's prove that context-free languages are closed under union. We are given L1 context-free languages with its grammar G1, and we are given L2 with a context-free language with its grammar G2, such that V1 intersection with V2 is an empty set, so we are talking about different names of the variables. We can construct the union of the grammar by merging the grammars. So G of the union will be V1 union V2 union with new start variable S, alphabet sigma 1 union with sigma 2. The new starting symbol will be the new variable S. We will use all the production rules of the first grammar and all the production rules of the second grammar, and we will have additional rule S derives S1 or S2, where S1 is the starting variable of the first language and S2 is the starting variable of the second language. The proof idea will be relatively simple. The rule S derives S1 or S2 enables a string W to be derived either from S1 and belong to language L1 or from S2 and belong to language L2. Let's see an example. We are given language L1, A in power of n, B in power of n. The grammar will have the following rules. S1 derives A, S1B or epsilon. Language L2 will be WW reverse. S2 derives A, S2A, B, S2B or epsilon. The union of those languages is the new language L. A in power of n, B in power of n, union with WW reverse. The new grammar will be S derives S1 or S2, and then all the rules of S1 and all the rules that can be derived from S2. Okay, let's move to the next operation, concatenation. Context-free languages are closed under concatenation. We are given L1 context-free language with its grammar G1. We are given L2 a context-free language and its grammar G2. Once again, we assume that V1 and V2 intersection between V1 and V2 is an empty set. So we use different variables names and we can construct the grammar of concatenation in the following way. We will use all the variables of the first grammar and the second grammar, V1 union V2, and we will add additional variable S. The alphabet, the terminal symbols of both grammars should be united. S1 union, sigma 1 union sigma 2. The new starting state will be S, and we will use all the rules of the first grammar, all the rules of the second grammar, and we will add additional rule of the concatenation. S derives S1 concatenation S2, where from S1 we will derive some prefix U that belongs to L1, and where from S2 we will derive some suffix V that belongs to L2, and all the words in our new language, all the word W can be divided to prefix U, which is derived from S1, and suffix V that can be derived from S2. We will use previous languages and previous grammar as an example. The concatenation result or the new language will be A in power of n, B in power of n, concatenation with WW reverse. The new grammar will be S derives S1 concatenation S2, and then all the rules of S1 and all the rules of S2. Next operation will be clean star. The context-free languages are closed under clean star operation. Once again, we are given a language L1 and its grammar G, and we would like to construct a new grammar G star for the language L1 star. The new grammar will have all the variables that previous grammar had with additional new variable S. The alphabet will be the same one. The starting symbol will be the new variable S. We will use all the rules of the previous grammar and we will add two additional rules. S derives S1 concatenation with S, where S1 is a starting symbol of the previous grammar, and S derives epsilon, since now in L1 star we definitely have an empty word as a legal word. Okay, the proof idea of what we did is actually a very simple one. The rule S derives S1 concatenation S means that some word W will be derived from S1, and then we can continue with the new word derived from S, and we will continue with concatenation as many times as we want. The rule S derives an empty word. The meaning is that we derive an empty word. And now in clean star operation, an empty word is a legal string of the language. see an example. We will use as the first language of the previous example. L is a in power of n, b in power of n. We will use the rules S1 derives a, S1b, or epsilon. Now the star operation language will be a in power of n, b in power of n star. And S we will derive S1 concatenation S or epsilon, and then we will add all the rules that are used to derive the rest of the language from S1. Okay, let's define additional closure properties of context-free languages. Context-free languages are not closed under intersection operation. Context-free languages are not closed under complement. Context-free languages are not closed under different. Context-free languages are closed under intersection with regular languages. Some of this corollary we will prove at class during our practice meetings. Some you will prove during homework. Let's talk about additional closure properties. Let's talk about substitution. Substitution means that we associate each terminal, sigma, from our alphabet with the language L sigma, which can be computed as some function h on the letter sigma. Given a word W, which has k letters, sigma 1, sigma 2, sigma 3, sigma k, the substitution h on the word W will be W1 concatenation with W2 concatenation with WK, where WI is a word belonging to the language of sigma I. For the language L, we define the substitution function of the language L in the following way. We take each word W of L and we compute H on W. The resulting language, AH over W, is the substitution language. Regular substitution. Every L sigma is a regular language. Context-free substitution. Every L sigma is a context-free language. So we can talk about regular substitution and context-free substitution. Let's see some examples of substitution. Example for regular substitution. We are giving a regular language L, A, B star. We define H of A be equal to A plus C star. And we defined H of B substitution for B, B0, 0, 1. If we want to construct, to define HL, H of L will be A plus C star concatenation with 0, 0, 1 star. If the original word of language L was AB, now we have A001, C001, AA001, CA001, and additional permutation as a subset of HW. Okay, let's see an example for context-free substitution. We are given a context-free language L. L equals 0 in power of n, 1 in power of n greater equal to 0. We can define substitution function h0 as a new language, a in power of n, 0, b in power of n, where n greater equal to 0. And we can define the substitution function h for 1 to be equal to 1. We were given an original grammar G that derives 0 in power of n, 1 in power of n. The original grammar was S derives 0 as 1 or epsilon. Now, when we use a substitution for H0, each 0 can be substituted with S0, and from S0 we will derive a context-free language A in power of n, 0, b in power of n. So S0 derives A S0 B O 0, and H1 is actually 1. The resulting grammar after the substitution H of G will be S derives S0 S1 or epsilon. S0 derives A S0B or 0. Let's talk a little bit more about regular substitution. We will use the following proposition. The regular languages are closed under a regular substitution, and we will prove this proposition. Let L be generated by some regular expression S, and for each letter A in sigma, let LA be generated by some regular expression RA. For each letter A that belongs to sigma, substitute each occurrence of A in S in original regular expression with RA. The resulting expression is a legitimate regular expression. Therefore, we actually proved that regular languages are closed under regular substitution. Now let's prove the proposition number 2 for context-free languages. The context-free languages are closed under context-free substitution. Let's prove this proposition. Let L be generated by some context-free grammar G. And for each letter A in sigma, let LA be generated by some context-free grammar GA. Each production rule R in the original context-free grammar, and each letter A in sigma can be replaced in the original production rule with a new variable SA, which is a starting variable of the new grammar GA. So each time...
שלום לכולם, התכנסנו.
Let's prove the proposition number 2. The context-free languages are closed under context-free substitution. The proof will be the following one. Let L be generated by context-free grammar G. And for each letter A of the alphabet, let LA be generated by some grammar GA. In each production rule R of the original grammar, each time we meet the symbol A, we will replace the symbol A with SA, the starting symbol of the new grammar GA. And we will do it for each letter of the alphabet. We will add VA, sigma A, and RA to the original grammar, and we will unite all the variables, terminals, and rules. The resulting grammar in any way is a context-free grammar. Here you can see the set of exercises that we will do during our practice meetings. We will use or closure operations or substitute operations to prove that some languages are context-free languages or not context-free languages. Let's talk how can we simplify grammars. A simplified form of the grammar is the grammar that doesn't have empty production rules, only S derives an empty word is permitted, and does not have unit rules. An epsilon rule is a rule of the form some variable A derives an empty word. A unit rule is a rule of the form variable A derives a variable B without any additional symbols. Every context-free grammar can be rewritten in a simplified form. We will study how to eliminate an epsilon rule and a unit rule in a few moments. The following algorithm can be used to convert context-free grammar to simplified grammar. Step number 1, we will remove all epsilon rules. I will explain how to remove epsilon rules in a few moments. A context-free grammar that does not have epsilon can be written without the context grammar that does not have epsilon can be rewritten without epsilon. But if epsilon belongs to L, then we remove epsilon from L. We will build a simplified form of the context-free grammar without epsilon rule. And at the end, we will add a rule as cap derives S or epsilon since epsilon belongs to the language. The next step after removing all epsilon rules will be removing unit rules. Once again, I will explain the technique in a few moments. Any context-free grammar can be rewritten without unit rules. So, step number 1 will be removing epsilon rules. We will find an epsilon rule, A derives epsilon, where S is not S, and remove it from original rules or from the set of original rules R. For each rule in R of the form B derives alpha A better, where R A, as you remember, can derive an empty word, we should add a new rule to R. B derives alpha concatenation better without A. A is now replaced with an empty word. So, if we have A at the right hand side several times, we rewrite or we add several new rules. For example, if we had the rule B derives alpha A concatenation BA gamma, we add to the original rule new rule where we eliminated the first A, alpha beta A gamma. Then we eliminate the second A and we will have the rule alpha A beta gamma, and then we will delete both A's, and we will have a new rule alpha beta gamma. If we have a unit rule B derives A and now A should be replaced by an epsilon, we add a new rule B derives epsilon to the grammar. We continue with step number 1 until we eliminate all epsilon rules from the grammar. Step number 2, we should remove all unit rules. For each unit rule A derives B, we will once again remove this rule from the original set of rules R, and we will add all productions of B to A. So if we had a production rule B derives alpha, now we will add this rule to A. A, instead of deriving B, will derive the right-hand side of B, will derive alpha. And we will repeat step number 1 until all unit rules are removed. So let's see some examples. Example of removing epsilon rules. We are giving a grammar and we have epsilon rule, B derives epsilon. We will start by asking ourselves a question: does an empty word belong to the language L, the language of this grammar? Since sense derives S, the starting symbol, derives A and some variables, but we definitely have a terminal symbol L, A, we know that an empty word does not belong to the language. Therefore, we do not need to add the rule S cap derives S or epsilon. Now we continue. After removing B derives epsilon, we should add additional rules where B are replaced by the epsilon. So we had B at the right hand side of the production rule S derives AB, now we can eliminate B and we can add a new rule A, terminal A, concatenation with variable A. Since we had a rule A derives B, once again B should replace by epsilon, therefore we should add additional rule A derives epsilon, and we also had B at the right hand side of the rule B derives small terminal B concatenation with variable B. Now variable B can be replaced with epsilon, so we add a new rule B derives small terminal b. But now after eliminating the rule B derives epsilon, we have an additional epsilon rule. And now during the second iteration, we will remove this rule. So we will replace A at the right hand side with an epsilon. So once again, we should start with taking all the rules where A was at the right hand side. And we will replace A at the rule S derives small a, AB. And we will add at the right hand side AB, where the variable A is replaced by epsilon. Also, we will use the rule S derives terminal A variable A. And once again, we replace variable A by epsilon. So we add S derives a small a. We will add A derives terminal A to the A, since we had the rule A derives variable terminal A concatenation with variable A, and in B we don't have any changes. So now in this grammar we don't have any epsilon rules. We managed to eliminate all epsilon rules. Let's see an example how we remove unit rules. We are giving a language where we have several unit rules. We have S derives A unit rule, A derives B, also a unit rule. We will start with the rule A derives B and we will eliminate it, delete it from our grammar. But we will add new rules where A derives right parts that can be derived from B. So we add to A derives BB or A. Since we had B derives BB or A, we now add those two productions to A. Iteration number 2. We will replace the unit rule S derives A. We will take a right hand side of A and add it to S. We will add S derives terminal B variable B or A or B or B once again. But since twice B doesn't give us any additional information, we won't write the same rule twice. So we will have S derives BB or A or B. Okay, now we will start talking about normal form of the grammar. There are several normal forms of the grammar. Chomsky normal form is one of the normal forms that we will study during the course. Chomsky normal form, abbreviation CNF, definition. A context-free grammar is in context normal form if every rule is of the form variable A derives two variables B, C, or variable A derives a single letter sigma, where sigma belongs to the alphabet, A, B, and C are variables. B and C uh, not equal to the starting symbol S. If a language contains an empty word, then S derives epsilon is allowed and you can use it in Chomsky normal form. Several words about Noam Chomsky. Noam Chomsky was American linguist, philosopher. He was a lecturer professor at MIT, and he is well known in the scientific community as one of the fathers of the more modern linguistics. Now let's continue with Chomsky normal form. A grammar rewritten to Chomsky normal form will have a binary tree as a parsing tree. Since each variable now derives only two variables or terminal symbols, we will be talking about binary tree. We also know that if we are given a string of the length n, the string will be derived in L in 2n minus 1 steps. We will build a tree, a binary tree with all the variables, and then all the variables will be replaced by a single letter, and we had n letters. Why binary tree and why Chomsky normal form is important? Because sometimes in programming languages you have binary tree predefined in the language. Therefore, if you can rewrite your grammar in Chomsky normal form, you can use given algorithms for binary tree to construct a parsing tree for some word and so on. Okay. The next theorem will be any context-free language can be generated by a Chomsky normal form grammar. Let's talk how we can convert context-free grammar to Chomsky normal form grammar. First, we will add a new starting symbol escape, and the new rule escape derives S to context-free grammar. We will remove all epsilon rules. We will remove all unit rules, and then we will convert all remaining rules into a proper form. The proper form means that we will replace each terminal symbol sigma I in the rule whose right hand side has two or more symbols into variable AI, where from variable AI we will derive this letter sigma I. For each rule of the form A derives several variables at the right hand side, b1, b2, bn, where n greater than 2, we will replace this rule by the two following rules. A will derive b1 with additional variable c1. From c1, we will derive the rest of the rule, b2, b3, bn. We will repeat step number 4 until we have rules with the right hand side greater than 2. We will stop running the algorithm when we will have all the rules at the right hand side in a correct form. Correct form means each rule derives or only two variables or one single letter of the alphabet. Let's start with an example. We are given a context-free grammar and we are asked to rewrite it in Chomsky normal form. First of all, we ask ourselves, does an empty word belongs to this language? No. If not, we don't need to add an empty word to the grammar. Do we have an epsilon rules which should be eliminated? No. Do we have a union rules? Yes. So we should eliminate unit rules. And we have several unit rules. S derives A derives S, B derives A. So we add a new rule, S cap derives S without epsilon, since we don't have epsilon. And now we start the elimination of unit rules. The first rule that we will eliminate is A derives S. Once again, we will replace S with the right-hand side that can be derived from S. So we will have A derives A or 0b0 or 1. Since A derives A has no sense, we eliminate this rule. Okay, we continue. The next rule we will remove is B derives A. So once again, we will replace A at the right-hand side by all the productions of A. So we will add to B the production 0b0, 1, and we will also keep the original production 0. Okay, we will continue, and the next rule we will remove is S derives A. Once again, we will replace A with the right-hand side. So we will have S derives 0b0, 1, or 0b0. Since we had the same rule twice at the right-hand side, one of the repetitions should be eliminated. The last unit rule is S cap derives S. So we will remove it once again by replacing S with its right-hand side, 0b0 and 1. Now please pay attention. If I start my derivation of words from S cap, I can reach a variable b. If I'm using variable b, I can reach only variable b. Therefore, I have two variables, s and a, which are not accessible, and I can delete s and a, and the resulting grammar without unit rules will be S cap derives 1, 0b0, b derives 0b0, 1 or 0. So now let's try to convert this grammar to the Chomsky normal form. Once again, we are looking at all the rules where we have two or more elements. So we are looking and we replace each terminal symbol by a new variable called, let's say for 0 it will be S0, for 1 it can be S1, but we don't need S1. So we rewrite the grammar. So S cap derives 1 or S0 B S0. B derives S0 B S0 1 or 0. S0 derives a single 0. Now we are looking at all the rules with more than two variables, and we should rewrite them with only two variables. So S cap will derive S0C. From C we will continue and derive B concatenation with S0. The same variable C will be used to simplify the rule B derives S0 B S0. We will replace it with B derives S0 C, and from C we once again will derive B S0. Now the rules written at the corner of this slide is the original grammar rewritten into Chomsky normal form. Our last topic for today is Chomsky hierarchy. One of the things that Noam Chomsky did, he explained or he proved that we have hierarchy of grammars. And Noam Chomsky defined several types of grammar: regular grammars, context-free grammars, context-sensitive grammars, and recursively enumerable grammars. So the first grammar, regular grammar, is the most restricted one. The regular grammar, according to Chomsky, uses the following rules. S derives sigma or S derives sigma b, where sigma is the letter of the alphabet and S and B are variables. Please pay attention that it's a little bit different than our uh, definition. This grammar generates regular languages. Regular languages can be decided by a finite automaton. The next type of grammars is context-free grammars. Here we have the following restriction to the rule. We have only one variable at the left-hand side, but A can derive alpha, where alpha can be a union of several variables or terminal symbols. This language is called context-free language. And during the next lecture, we will study additional computational model, which is called push-down automaton, and context-free language can be decided by a push-down automaton. Additional type of the grammar that Noam Chomsky described is content-sensitive grammars. In this grammar, we don't have only one variable at the left-hand side. We have some prefix alpha, a, some suffix beta. And if around a we have a alpha and beta, we can derive a derives alpha, gamma, beta. So basically, we replace a with gamma if and only if we can see alpha and beta around a. The language of this grammar called content-sensitive language because we are looking at the contents before A and after A or before A or after A. And it can be decided by a linear bounded non-deterministic Turing machine that we don't study during this semester, but you will study it during your next course. Let's see an example for the context-sensitive grammar. Please pay attention. We are given a grammar for the language n power of n, b in power of n, where n greater equals to 1. This language, by the way, is context-free language, but it can be written with content-sensitive grammar. Please pay attention that now on the left-hand side of the rules, sometimes you have not one variable, but two variables or terminal symbol and variable. So let's see the following parsing tree and let's derive the string a in power of 2, b in power of 2. So we will use the first rule and s will derive a, s, b, c. And then we will use the third rule and we will replace as with its right hand side abc. Now we will take two symbols, terminal b and variable c, and we will use the Rust rule and we will derive the terminal b. Now we will take terminal b with variable b and we will use the rule terminal b variable b and derive two terminal bb. Now once again we will use rule b c and we will derive a single b. Now we finished with all variables. So the word written at the leaves of the tree is AABB, which is A in power of 2, B in power of 2. Okay, the last type of the grammar is recursively enumerable grammar. You don't have any restriction on rules. Anything can be found on the left-hand side and right-hand side. The language generated by this grammar is called recursively enumerable language, and it can be decided by a general Turing machine which once again you will study during the next course. Thank you very much for listening. We finished Unit 7, we finished Lecture 9. We will meet during Zoom practice meetings. We will practice some questions. Next week, we will continue with push-down automata.